Welcome back all of you to the fifth and the last video of water chemistry and sewage water treatment. Hope all of you are doing good. Well, in today's class, we are going to cover two sewage water treatment processes, trickling water filter process, which is an aerobic process, UASB, which is an anaerobic process. We'll also be covering significance and estimation of dissolved oxygen, COD, and BOD. Now, straight to the class. Syllabus, as I said earlier, has been divided into 8 parts for convenience, and we have covered already 6 of them. Today in this video, we are going to cover the 7th and the 8th part. Dissolved oxygen estimation by Winkler's method, BOD, COD, estimation, significance, and also their definition. Then sewage water treatment, under that a flow chart diagram showing the preliminary, primary, secondary and tertiary methods, and in detail trickling filter process and UASB. And here we are moving on to water, part 5. What you see in this picture is one of the greatest challenges that we face today, water pollution, and that too because of the sewage water. So here we are going to discuss about what steps should be taken to treat the sewage water before it is let out to the running water bodies? Well guys, here we are at sewage water treatment. We are going to see that in brief. The main aim of sewage water treatment is to reduce the high BOD of the sewage water to low permitted levels of BOD. BOD, you may be knowing, is a very important parameter in determining the extent of pollution present in water. High BOD means highly polluted water. So we are now going to lower the BOD to permitted levels through a series of treatment processes. And all these treatment processes put together will form the sewage water treatment. Well, here we are going to discuss 4 steps of sewage water treatment. Step number 1, preliminary treatment process. Step number 2, primary treatment. Step number 3, secondary treatment. And step number 4, tertiary treatment. I repeat, preliminary treatment, primary treatment, secondary treatment and tertiary treatment. Now let's have a look at the preliminary treatment. In preliminary process, we are going to screen the large floating materials, suspended impurities or inorganic matter, even oily impurities present in the water using bar and mesh screens or grit chambers or skimmers, etc. Okay, so we have now removed all the floating or inorganic or oily matter. Now, once the screening is over, we are going to send it to the primary treatment. What is primary treatment? Remember, it is sedimentation. Sedimentation means the screened water is allowed to stand in huge tanks for hours so that the organic matter will slowly settle down. Well, if the size of the organic matter is very small, it may take longer time to settle down. In order to accelerate the process, we will add certain coagulants which will form flocculation with the particles, and such chemicals, for example alum, are added, and the sedimentation process is over. Once the sedimentation process is over, you can see the filtrate and the sludge, that is the residue, separated. Now what are we going to do? We are going to send them for secondary treatment separately, sludge separately and filtrate separately. Now remember, secondary process is a biological treatment process. That means they are sent for biological treatment. Well, here it is. The filtrate is sent for an aerobic process. That means we are making use of aerobic microorganisms. For example, trickling water filter process, active sludge method, etc. And what about the residue of the sludge? That is sent for an anaerobic process, making use of anaerobic microorganisms. Example, UASB. Well, we will be dealing with these both these processes in detail in the coming slides. Now, once the secondary treatment is over, we are sending them for tertiary treatment. What is that? Well, this involves the removal of nitrogen, maybe in the form of ammonia. Nitrogen will be present, and phosphorus, that is removed through a process called precipitation. Nitrogen is removed through a process called nitrogen stripping, and any microorganisms left will be removed. We have already seen chlorination, etc. That is called a disinfection. So that is the process: preliminary process, primary treatment, secondary process, tertiary process. And all these four processes put together will make the sewage water treatment. Well, here you are going to get a consolidated picture of a flow chart of the whole thing that we have seen. Here you are. Screening, that is the preliminary process. And then once the screening is done, we are sending it for a primary process of sedimentation. The filtrate and the residue or the sludge are separated. And then we are going to send them for the biological process or the secondary process, aerobic. Filtrate sent for aerobic, activated sludge or trickling filter. Residue sent for anaerobic process, example UASB. And finally, the tertiary process of precipitation, nitrogen stripping and chlorination, that is disinfection, can be done. As I said, we are going to see the secondary treatment in detail. This is a biological process. This is done in order to remove the organic waste and the nutrient matter that is left in the water even after the primary treatment. Well, the primary treatment is the sedimentation process. After that, the filtrate and the sludge is separated. The filtrate is sent for aerobic treatment. Example, trickling filter process, active sludge method. And the sludge is sent for anaerobic process, that is UASB. Let us see it in detail now. Here is a comparison of aerobic process and anaerobic process so that we can understand them better. Well, aerobic is happening in the presence of plenty of oxygen, whereas anaerobic in limited supply of oxygen. Now, aerobic makes use of aerobic bacteria, anaerobic process makes use of anaerobic bacteria. In aerobic process, there won't be any bad odor, but anaerobic process is followed by bad odor, unpleasant odor. Now, what about the oxidation products? If it is aerobic oxidation, carbohydrates, which contains plenty of carbon and hydrogen, will be oxidized to carbon dioxide, hydrogen to water. Whereas in the case of anaerobic process, mainly carbon will be oxidized to methane, CH4, hydrogen rich, not oxygen rich. Well, this methane can be used as a biogas. It is a biogas. Whereas in aerobic bacteria, no methane is produced, so no biogas fuel is formed. Now, considering the last point, we are just considering in general few oxidation products. In the case of aerobic oxidation, carbon is oxidized to carbon dioxide, hydrogen to water, phosphorus to phosphate, nitrogen to nitrate, sulfur to sulfate. 8 means rich in oxygen. Well, coming to this side, carbon to methane, phosphorus to phosphine, nitrogen to ammonia, sulfur to hydrogen sulfate. So instead of oxygen combined products, you are getting hydrogen combined products. So this is a comparison between aerobic and anaerobic process. This is a K2 question also. So please remember this one. It is important. Now on to trickling filter method. It's a secondary sewage treatment method and it is also a biological aerobic treatment. We're going to see that in detail. Let us now have a look at the chemical reactions involved in trickling water filter process. We know that this is an aerobic oxidation process and we are trying to remove the organic waste as well as nutrients present. The organic waste, which are rich in carbon, will be converted to carbon dioxide. And the nutrients which are rich in nitrogen will be converted ultimately to nitrates. Here it is. The carbon, this is urea, NH2CO, NH2 getting converted to carbon dioxide and ammonia forming acids first, nitrous acid and nitric acid, and finally nitrates. These are a few chemical reactions involved. Aha, please take a good look. This is the equipment in which all these reactions are happening. Now we will be seeing the process in detail in the coming slide. Well, now on to the real process of aerobic oxidation. Well, this process happens, let us say, in 3 steps. First is the preparation of the filter bed. Second one is the introduction of the sewage. And third step is the aerobic oxidation. Well, let us start with the first one, that is preparation of the trickling filter bed. Now you can see cross lines here, okay? And this is a 2-meter deep pit in which we are filling broken bricks, crushed rocks, chips, etc. Since they are in the crushed form, they will be having high surface area. We are going to feed the aerobic microbes onto them. So in the 2-meter deep filter bed, colonies of aerobic microbes like bacteria, fungi, protozoans are grown, and this will act as a biological filter. So the biological filter is now ready. Now we have to introduce the sewage water. Now how do you introduce the sewage water? It is introduced from the bottom. You can see it is introduced through one hole and air is introduced through the other one. So here sewage filtrate and air enter from the bottom and they flow up. Now listen to me how it is entering the trickling reactor. Just imagine you are placing an open umbrella right at the middle of your filter bed. Okay. And the umbrella is constantly rotating. We are rotating the umbrella. Well, now the water as well as the air is moving up through the hollow stem of the umbrella. Okay. And it moves up and it reaches the rotating arms of the umbrella. And here there are too many holes. And through the holes, the sewage water will be trickling down. Not that word. Trickling down through the bed, or they're sprayed down through the bed. That's it. Once they are coming down or filtering down or percolating down through the bed, what happens? What is there in wait for them? There are enough and more microbes, colonies of microbes which are very hungry, hungrily waiting for their food. And the sewage water is coming rich in organic matter. So immediately the bacteria will start feeding on the organic matter present. And they degrade them, they decompose them, they decay them aerobically in the presence of oxygen. And once this process is over, all the organic matter will be consumed by the bacteria and the treated water will be coming down. See, it is trickling down through the rotating arms over the bed and oxidation happens. Aerobically, microbes degrade the organic matter and the treated water finally comes out through the outlet. And this is now sent for tertiary treatment like disinfection process, etc. Nitrogen stripping or phosphorus precipitation, etc. Almost 90% of the BODs claim to have been removed through this process. Okay, so that is about the process or the functioning of trickling filter bed. Here we have another aerobic water treatment process, activated sludge method. As you can see, the biological reactor, this is also a biological process. The biological reactor has an air tank as well as a clarifier or a settler. The air tank contains sludge, air, as well as aerobic microorganisms. The raw water, the sewage water is fed into the air tank. Here the treatment is happening. Relatively, it is a faster process because of the uniform dispersal here. And then the treated water is sent to the clarifier or settler for removing any kinds of waste matter that will be settling here. The excess sludge can be removed and the treated water is taken out. Okay. So far we have seen aerobic treatment processes. Now we are at UASB, which is an anaerobic process. Upflow anaerobic sludge blanket, UASB. This is a secondary sewage water treatment as in the previous cases, but it is a biological anaerobic process. Here you have the picture of an anaerobic digester or UASB reactor, let us say, the equipment that is used for the anaerobic treatment of water. In the coming slide, we will see how this functions. Upflow anaerobic sludge blanket or UASB. Well, as the name indicates, each term will be explaining the functioning of the blanket as you are going to see now. Please look at the picture. You can see sludge granules kept in a suspended manner inside the reactor. Well, on the surface of these sludge granules, we are now going to grow the anaerobic bacteria. and there they will grow and they will multiply rapidly, forming a granular sludge blanket. This process will take about 3 months for acquiring maturity. Now, one thing you have to remember, the retention time, or let us say the efficiency of the reactor, will depend on few factors like maturity of the bacteria, the type of bacteria used, temperature inside the reactor, etc. So it is an important factor. Now what are we going to do? Once it acquires maturity, we are going to let in the effluent. As I am showing here, effluent is coming in. That is the sewage residue. Yes, the sewage residue flows upwards. That is the reason why we call it upflow. Anaerobic you already know, and the sludge blanket is formed. Okay, so the water is coming inside and there they are meeting the bacteria on the sludge granule. The bacteria are very hungry. They want to feed on the organic waste present in the effluent. That is exactly what they're doing. The bacteria on the sludge blanket degrade the organic waste in the sewage. And in this process, what is coming out as the product? Is it carbon dioxide? No. That is only happening in the aerobic process. Here there's no oxygen, so you don't get carbon dioxide. Carbon gets converted into what? Methane, CH4. Gases like methane are produced and these are used as biogas, which are tapped from the top. The gas is tapped from the top and is used for the functioning of the UASB itself. So it's a typical case of recycling also. And the treated water is coming out through the outlet. So that is how the upflow anaerobic sludge blanket functions. I have included a few KTU questions here which you can go through later, and also please note that I have included the answers of all these questions in the study materials which I have uploaded in the ERP. Now this slide will give you a consolidated picture of the main water treatment processes that we have covered. Hardness removal through ion exchange process, desalination through reverse osmosis, and domestic water treatment. One major step was disinfection through chlorination, UV radiation, and also sewage water treatment. Two major steps in the secondary process was trickling filter process and UASB. All these are important. Well, now we are moving on to the next portion, that is dissolved oxygen. Winkler's method of estimation will be covered, and BOD and COD. We will be covering definition, estimation, and significance. Okay. Dissolved oxygen, let us see in detail what is it. By definition, it is the free dissolved oxygen molecule. Why I said molecule? Because it is not in the combined form. We are talking about the absolute oxygen molecule alone. So it is a free dissolved oxygen molecule in water in the uncombined form. Normally 6 to 8 ppm is the allowed quantity. And if this much water, the oxygen is present in the water, that is the reason for the existence of aquatic life, because they can breathe on the dissolved oxygen present. Well, for this reason and for many other reasons, we can say that dissolved oxygen is a parameter. It's an important parameter that determines the quality of water. If the dissolved oxygen in a water body is less, that means it is highly polluted. Low dissolved oxygen means high BOD. We will be seeing that soon. That means high pollution. Okay. It is important to know the factors that affect dissolved oxygen present in water. I have listed at least 4 factors here: temperature, pressure, turbulence, and amount of waste. Well, as the temperature increases, we know that all gases will have a tendency to escape. So is the case with dissolved oxygen. As the temperature increases, dissolved oxygen decreases, downward arrow. And as the pressure increases, dissolved oxygen increases, upward arrow. Turbulence has a similar effect. As turbulence increases, dissolved oxygen increases. More currents, more movements, dissolved oxygen increases. The amount of waste, dissolved oxygen decreases. That means when waste is more, decaying is more, degradation is more, consuming the dissolved oxygen, and dissolved oxygen decreases. In fact, less dissolved oxygen is an indicator for more pollution also. Winkler's method. Well, this is one method which is going to help us in estimating the dissolved oxygen present in the water sample. This is a titrometric method. For any titration, we need one reagent in the conical flask and a second reagent in the burette and an indicator. Well, here, the reagent in the conical flask is the sample water whose dissolved oxygen is to be found. And in the burette, we are taking standard sodium thiosulfate. And the indicator used is starch solution, starch. Well, now to the procedure. Before we take the water sample, it has to be treated with certain chemicals so that it can be titrated against sodium thiosulfate. Let us have a look. We are taking 250 ml of sample water whose dissolved oxygen is to be found in what? In a glass bottle with airtight stopper. This is very important because we have to see that no air bubble enters the water. Okay. Now, once it is taken, we add two reagents. What are they? 2 ml manganese sulfate and 2 ml alkaline potassium hydrate to this one. Then we stop the bottle, close the bottle with the stopper, and without any air bubbles forming inside, we shake it well and we can see a precipitate, a flock forming inside the. Now we allow that to settle, and once the flock formation is complete, we want to dissolve it. How do we dissolve that? 2 ml of concentrated sulfuric acid is now added to this one and again shaken well. All the precipitate dissolves and the water, sample water, is now ready for titration. Okay. Now for the titration, we are going to take 100 ml of water out of this into the conical flask. And it is titrated against, we know against what? Standard thiosulfate taken in the burette. And starch solution is used as the indicator, and from the titer value we can find the dissolved oxygen. So that is the procedure or the Winkler's method. Just a pictorial representation of the same thing again. The stopper bottle, water taken, added manganese sulfate, then alkaline Ki, and here we are shaking it well. Flock is formed. We are adding concentrated sulfuric acid to dissolve the flock. We are shaking it well, again stoppering it and transferring an amount about 100 ml to a conical flask. We are adding starch and then we are titrating it against standard thiosulfate, and the titer value is noted, and from the titer value we can find the dissolved oxygen. Okay. On to the next topic. Here we are considering two important parameters in deciding the extent of water pollution, and they are very familiar to us: BOD and COD, biological oxygen demand or biochemical oxygen demand, and here it is chemical oxygen demand. And we know that BOD is much lesser than COD or COD is higher than BOD. Let us get into the details. Let's consider the definition of BOD or biological oxygen demand of a sample polluted water. Well, it is the amount of free dissolved oxygen consumed by microorganisms present in 1 liter of water in decomposing biologically oxidizable organic matter within a period of 5 days at 20 degrees centigrade under aerobic conditions. So this is a definition. Let me try to explain it now. Take 1 liter of the polluted water. The water will contain organic waste as well as microorganisms in that. And the microorganisms will decay the organic matter. But for this process, this is an aerobic process. For this process, oxygen is required. From where does the microorganisms get the oxygen? From the water itself, because we know that there is free dissolved oxygen present in the water, right? So that amount of oxygen is called oxygen demand. The amount of free dissolved oxygen consumed by microorganisms present in 1 liter of water for what? For decomposing the biologically oxidizable organic matter. Now, this usually takes a duration of 5 days and the optimum temperature is 20 degrees centigrade. So, within a period of 5 days at 20 degrees centigrade under aerobic condition, that we already know because it makes use of oxygen here. So that makes the definition of BOD. So understanding this concept clearly, if you go through the definition again, it will be very easy for you. Okay. Now, free dissolved oxygen is the most important term because it is getting all the oxygen from the dissolved oxygen, not from any other source. BOD is highly significant, we know that. So let's have a look at the significance of BOD. Well, first of all, it gives us an idea about the extent of pollution in the water bodies. And also it tells us if the water is causing any threat to the aquatic life or not. Is there enough dissolved oxygen in the water or not? So that also we come to know from the BOD value. And also it tells the authority whether the quality of an effluent is good enough for dumping it into the running water bodies. So before dumping the effluent water, the quality check is being done by estimating the BOD content of the water. Now here is a question to be done. So please take your pen and paper and get ready for the tutorial session. Calculate the BOD of the water sample containing 75 milligrams per liter of CH2O. Okay. The water sample contains 75 milligrams per liter of the organic pollutant CH2O. What is the BOD? That is a question. BOD means oxygen demand. So the first step in such cases is just write down an equation between the pollutant and oxygen to find out the oxygen demand. Like this, CH2O plus oxygen giving carbon gets converted to carbon dioxide, hydrogen plus converted to water, and no other element is left. So you are happy with this equation. Just write down such an equation. Okay. Now balance it. This is an already balanced equation, so you don't have to bother. So we know that 1 mole of CH2O demands 1 mole of oxygen in this as per this equation. So now let us calculate the gram molecular weight. Carbon 12, hydrogen 2 plus oxygen 16. So that means 30 AMU of oxygen is 30 AMU of CH2O demands 1 molar oxygen means 2 into 16, that is 32 AMU. Same in terms of milligrams, 38 milligrams of CH2O demands 32 milligrams of oxygen. What is the question asked? What is the BOD for 75 milligrams of CH2O? Easily we can find from this equation. If 30 milligrams of CH2O demands 32 milligrams of oxygen, 75 milligrams of CH2O will demand 32 by 30 into 75, that is 80 milligrams of oxygen, or BOD of CH2, 75 milligrams of CH2O is 80 milligrams per liter or 80 ppm. Estimation of BOD, what is the procedure? Well, we are taking a known volume of the sample water, say XML, and we are diluting it to YML. Okay, XML initial volume, YML final volume. Now we are going to divide the water sample into two, and they are taken in two separate stoppered bottles. Now, take the first stoppered bottle and find the dissolved oxygen in it immediately, even before the decay process starts, and that value is called the DO initial. And what about the second one? Second one, there's no hurry. We are allowing it to undergo complete decay of the organic matter over a period of 5 days at 20 degrees centigrade. We are allowing it to complete the process. After 5 days, when all the decaying is complete, we again take the sample and find how much dissolved oxygen is left after decaying. And that is called a DO final. Now you can find BOD by a simple equation. DO initial minus DO final into dilution factor. What is dilution factor? It is nothing but a ratio of Y and X. Y is the final volume, X is the initial volume. Yes. So Y by X is the dilution factor. And remember, in all these processes, dissolved oxygen was found by using Winkler's method, which we have already covered while we were discussing dissolved oxygen. Okay, so this is a simple procedure for finding the BOD. Well, even though BOD is a highly significant parameter, it has got its own limitations. The first one is it's a slow process. It takes 5 days, we know that. And the second one is, it does not assess all oxidizable impurities. Well, there can be organic impurities as well as inorganic impurities. Coming to organic impurities, it can degrade only biodegradable organic matter. There are also non-biodegradable organic matter like cellulose content, etc. This cannot be assessed by BOD. For example, sewage from rayon or paper pulp industry cannot be assessed by BOD. And now coming to inorganic waste, it does not assess oxidizable inorganic content in water at all. So these are few limitations of BOD. This has to be kept in mind. COD or chemical oxygen demand. Well, we have already seen the limitations of BOD. And because of those limitations, there is the necessity of another parameter which can give you a complete picture of the water pollution, and that is called chemical oxygen demand. Let us have a look at the definition. The amount of oxygen required for the oxidation of all kinds of, please note that, all kinds of chemically oxidizable organic and inorganic matter present in 1 liter of sewage water. 1 liter again, 1 liter of sewage water. Here, certain things have to be kept in mind. One is chemical oxidation is happening and we are using an oxidizing agent. We are not talking about free dissolved oxygen. We are providing oxygen using a chemical oxidizing agent. Okay. Now the second one is biodegradable, non-biodegradable and also chemically oxidizable substances are assessed here. That is the next point. And the third point is that it is highly fast. And since it includes more organic waste, COD value will be definitely higher than BOD value. So these are certain important points about COD. I hope it is clear. Well, here is a comparison of BOD and COD. This is a K2 question. In fact, if such a question comes, the first point should be the definition. We've already seen that, so I'm not going to repeat that. Now, the second point of comparison is the unit. Both the units are ppm. Comparison does not mean differences. It can be similarities also. So the units are ppm in both the cases. Now in BOD, we are considering biological oxidation. In COD, we are considering chemical oxidation. In BOD, we are considering only the degradation of biodegradable waste matter. Whereas in COD, we are considering both biodegradable as well as non-biodegradable. Also chemically degradable. Okay. Now, BOD is a slow process. It requires at least 5 days. COD, whereas, is a fast process. It requires only 3 hours or less. Now, BOD is lesser value. COD greater value. That is, COD is always greater than BOD. So this gives you a comparison of BOD and COD. Please remember, this is an important question for KTU also. About the significance of COD, we know that it gives an idea about the extent of pollution. Higher the COD, higher will be the pollution. And it covers or it assesses both biologically oxidizable and chemically oxidizable materials present in sewage water. So it is greater than BOD always. And it helps the authorities to assess the quality of industrial effluent. Industrial effluent, we all know that it does not just contain organic waste, it definitely mostly contain inorganic waste also. So it helps the authorities to assess the quality of the industrial wastewater better than BOD. And last but not the least, it's a fast process. So you don't have to wait for 5 days or more for the result to come. It gives you immediate result. A crisis comes at some point, then immediately the authorities get the result and they can take immediate action with the help of COD. That again is another significant factor. So these are few points. Estimation of COD. This is also a titration method. The only speciality is that we are going to conduct 2 parallel titrations here. First one with sample sewage water, second one with pure water. And then we take the titer values of both these titrations. Let it be V1 in the first case and V2 in the second case. You take the difference, V2 minus V1. From that, we can easily find the COD. So that is the idea. Now let us move on to the real procedure. In the first case, with the sewage water. Second one with the pure water. Okay. In the first case, we are taking VML of sewage water, a non-excess of potassium dichromate and dilute sulfuric acid. Why is it so? The sewage water has organic matter in that. The organic matter's oxygen demand is the one which we are estimating here. So there has to be an oxidizing agent which can provide oxygen for that. So here acidified dichromate is the oxidizing agent. This is taken in excess of what is needed. All these three reagents, sewage water, dichromate and sulfuric acid, is taken in measured quantities. Now, to make sure that the oxidation process is complete, we are going to reflex it for 2 hours. Then we cool it, and then a huge part of dichromate will be consumed for oxidation. But still, some dichromate will be remaining unreacted. This unreacted dichromate is now titrated against ferrous ammonium sulfate. Such titrations are called back titrations. Okay, so where unreacted reagent is used. So unreacted dichromate is actually titrated against the reagent taken in the burette, and that is standard ferrous ammonium sulfate. You now note the titer value. Let it be V1. Now, the second experiment has to be done, the same procedure with the same measured quantities of the reagents is conducted with pure water in the place of sewage water. Well, we know that pure water does not contain any organic waste. So, whatever dichromate is added to the solution will remain as such. It will be unreacted, and that unreacted potassium dichromate is now titrated against ferrous ammonium sulfate. The value is noted, which will be higher than V1, which is V2 here. So, take V2 minus V1 and COD is found. So, that is the idea here. Let us now have a look at the calculation involved in COD estimation. Well, the titration is between the sewage and ferrous ammonium sulfate FAS. We need to know the value of N sewage, that is the concentration of sewage, in order to find the COD. Okay, how do you find that? We have a universal equation for any titration, that is V1 N1 is equal to V2 N2. That here becomes V sewage into N sewage is equal to VFAS into NFAS, where FAS is ferrous ammonium sulfate. Okay. Now, if we know V sewage, which we already know because we have taken the VML, NFAS, that is also known to us, it is given. And VFAS, what is that? V2 minus V1, which we have seen in the previous slide. So, all these three factors are not, so we can easily find N sewage. V sewage into N sewage is equal to V2 minus V1 into NFAS, or N sewage is equal to, rearranging it, we get it as this. Once we know N sewage, how do you find COD? Well, COD, oxygen, so we have to consider the equivalent mass of oxygen here. Oxygen demand we are calculating, right? COD is equal to N sewage into 8. 8 is the equivalent mass of oxygen. Into 1000. Why 1000? In order to convert that into ppm or milligrams per liter. COD will be N sewage into 8 into 1000 milligrams per liter or ppm. Now to the practice sessions. Here I have given you 3 questions. Please do it by yourself. I have added the answers also here in brackets for your reference. So make sure that you are doing it. And if you have got any doubts after doing it, we can clear it during our online class. Okay, I'll soon be informing you when the online class is. But before that, please come prepared, do it, and we will clear the doubts then. Okay. With that, guys, we are coming to the end of this session. That is module on water chemistry and sewage water treatment. Here, as usual, I have a few questions, K2 questions for you. Please go through it later. And if you have any doubts, we will be dealing with all those doubts in the online class session. So till then, stay home, stay safe. Thank you.